I am Visweshwaran. I am a postdoctoral researcher and NCEO fellow from University of Reading, and I am working with Professor Sora Dance, who is also a part of NCEO and professor from University of Reading, and Elizabeth Cooper from UKCH. And the topic of my presentation is optimizing soil moisture assimilation strategies for improved predictions in JULES land surface model. So, Joint UK Land Environmental Simulator JULES is a community land surface model developed by Met Office, and which is predominantly used by agencies and the researchers in UK and across the world. And since the focus of my topic is on soil moisture, let me stick to it. And JULES assume four layers in its structure, with thin layers at the top and a very thick layer at the bottom. And the soil moisture V at the layer K is defined by the movement of the fluxes, vertical fluxes from the layer above and the below, given by W, and the root water uptake E. So to estimate the soil moisture V, JULES provides you with two options in its soil hydraulic module, and we have chosen Brooks and Curie method, which is defined by this equation, where if we know the saturation and the wilting point of the soil, and if we know the hydraulic properties, then we can estimate the soil moisture. But these information or the parameters are not easily available. So what we do is we use a simple soil function, also called as transfer function, and we have chosen Cosby transfer function here. And what it does is it converts easily measurable variables like soil texture information, such as percentage of silt, percentage of sand and clay. When you have this information, it transforms into these some of the soil hydraulic parameters which are quite difficult to measure. So the point here is, like, if we optimize these constants of the transfer function k1 to k12 here, then we can, using this set of equations, we can estimate these hydraulic properties, and then we can feed them into this Brooks and Curie to get the soil moisture. So JULES, like any other land surface model, are subjected to various sources of uncertainty. And as a data assimilation researchers, we try to blend two sources of information based on their respective error covariances to improve the estimates of the forecast of the model for various applications. And in this study, we have used ensemble variational hybrid assimilation approach, which is quite similar to 4D VAR, where we, within an assimilation window, we seek to minimize the cost function J, which is summarized by prior term and the observational term, where in the prior term we try to minimize this prior guess given the model error covariance matrix B, and the sum of all the discrepancies between the model trajectory and the observations given the observational error covariance matrix R. However, for models like JULES, which is complex, estimating the tangent linear model and hence the adjoint model, and also finding the inverse of the B matrix is quite cumbersome. So what we can do is, in ensemble variational approach, we can run the model in ensemble mode, and we can estimate the mean, and we can find the differences of each ensemble from the mean to get the perturbation vector, and we can replace this matrix B with the perturbation vector and its transpose using a concept called control variable transform. I'm not going to go into detail. The ultimate thing is we seek to optimize this control vector xb, which can come from state vector or a parameter vector or state parameter augmented vector, in such a way that the posterior model is much better than the prior model. So in this study, we have used Cosmos UK observation sites, which provides meteorological data, which is used for the JULES model forcings, and soil moisture, which is used for assimilation and validation purposes. And it estimates the soil moisture using cosmic ray neutron sensor. So how it works is, like, the incoming cosmic rays, when it interacts with the water molecule in the soil, it gets absorbed, and those that gets reflected back is absorbed by this CRNS sensor. And if there are more water molecule in the soil, if it is almost saturated, then most of this cosmic rays gets absorbed and very less gets reflected. So this inverse relationship is used to estimate the soil moisture at the peripheral or the field scale level, which is quite good. So we have used this soil moisture observations for 3 years: 2016 as a warm-up period, 17 as a data simulation run, and 18 as the forecast period. So we have chosen 16 locations across UK, and these locations were chosen considering the diverse nature of this soil characteristics and the land cover characteristics, where Some of these sites have high organic content in nature and few has calcareous in nature, to see how this JULES and also the data assimilation performs across these sites. So when we talk about JULES, the parameter estimation for the JULES has already been conducted by Cooper et al. 2021 and Pennington 2020. However, we performed this state parameter estimation as a first of its application for the JULES model, where in our study we have done three scenarios. In the first scenario, we have done this state estimation or the initial condition update at the January 1 of this assimilation period 2017. So as I have told before, there are four layers. So we will be having four initial conditions per site, and we have chosen 16 sites. So our state vector becomes 50 cross 64 for the first scenario. Whereas in the second scenario, we have done the parameter estimation, and those K1 to K12, those constants of the P-load transfer function, those we try to optimize. So our parameter vector is 50 cross 12. Whereas in the third scenario, we have augmented both the state and the parameter vector to obtain the state parameter vector, and which is around 50 cross 76. So coming to the result, here I'm showing you the time series of the soil moisture for 2017, which is assimilation period and forecast period, for two locations, Cardiff and Gisborne. And clearly from this, we can see that the posterior, which is represented by orange color, is capturing these observations quite well as compared to the blue, which is prior model run. And to understand this better, I have plotted this KGE matrix across all the 16 locations, which is summarized by the three terms or correlation: alpha, which is the variability in the observation, how much it is getting captured is captured by the variability in the model, which is alpha, and beta is the bias. So from these result, what we have observed is that as compared to the prior model run, which is blue color, all the three scenarios are actually performing better, one being the optimal value. And especially the third scenario, which is the state parameter case, is showing much better result than the other scenarios, and showing more than 0.8 for almost 7 to 8 locations during the assimilation period. And this kg improvement comes mostly from the changes which we have observed from this alpha and the beta component, where we can see the underbase nature of the JULES has been captured after the assimilation. And also, one of the advantage of using this state parameter over the parameter only case is that these are the changes which we have observed in the soil hydraulic parameters. Here I will focus just on one thing, which is VSAT, and this VSAT gives you how much soil can hold the water. And clearly we can see that in both the second scenario and the third scenario, we can see that the posterior values are much higher, meaning soil can hold more water in it. However, the difference is that the changes which we see between the prior and the posterior value are more pronounced in the second scenario, which made the JULES more dynamic or flashy. And this effect was moderated when we incorporated the initial condition in the state parameter vector. However, there was one limitation, which is when we did the state estimation or the updation of initial condition, we have observed that the effect of updated initial condition lasted only few months, up to 3 to 6 months, and after that the posterior values are almost same as that of the prior values. Here I'm showing you the soil moisture for two locations, Holland and Sheep. So to circumvent this, currently we are now working on a cyclic data assimilation scheme to update these initial conditions more frequently or more dynamically, let's say quarterly and half yearly update, to see how the JULES perform or JULES behave when we do this thing. It should be noted that the posterior PTF parameters K1 to K12, whatever we have derived from the previous work, that we have used it here. And these are some of the preliminary results of the data assimilation, cyclic data assimilation result. And left hand side and right hand side are the half yearly and quarterly update for the sheep side. And from visually we can see that as compared to the prior, the posterior soil moisture estimates are slightly closer to these observations. However, we cannot see a much big difference between the prior and the posterior. So here also I have plotted kg and p base values, and we can see that as compared to the prior, we can see the kg value has increased moderately, and also p base has decreased. However, there was no concrete difference between quarterly update or half yearly update, and still now we are figuring out what would be the optimal window length for updating this initial condition. We are trying for monthly update also. So this is a work in progress, and we are trying to figure out what will be the best for our work. So the ultimate goal is to create a kilometer scale reanalysis soil moisture product for the UK using this JULES data assimilation framework, which can be operationally used by UKCH and Met Office for their hydrological outlook portal. And as a first step, we have done the state parameter estimation for the 1D JULES model across 16 locations. And in the second step, now we are trying to find the optimal assimilation window length to perform the cyclic updation for the initial condition update. And in the third step, in future, we are planning to do a multivariate assimilation framework by incorporating both soil moisture and the stream flow information within this state parameter framework for the three-dimensional JULES model to see how it works. Yeah, thank you.